about space, and some of you may have noticed that. One is good and one is bad. Which one do you want me to mention first?
Good one.
The good one first? Okay, the good one is that you can buy a ticket to go to space for $250,000. Virgin Atlantic became public, and they are actually selling tickets. 600 people voted already. So starting next year, people will go into space, zero gravity, and just for the price of $250,000. And they plan to eventually have trips across the globe that will take 90 minutes or so, because that's the time, the characteristic dynamical time. So rather than taking half a day to get to distant locations, we will perhaps in 5 years, they say, we will be able to get there in a couple of hours. So that's the good news. Now, what is the bad news? The bad news is that, again, related to technology.
It's one-way ticket.
Sorry?
The ticket's only one way?
No, that's only on a trip to a black hole or to Mars. But the bad news for astronomy is that there is this new initiative by SpaceX and other industries to establish a lot of satellites in space. And in particular, there is a network called Starlink. There is an article about it in the New York Times today. And they are producing of the order of, they just launched 60 satellites this week. They're producing, they have permission to have 12,000 of them. And then they ask for 30,000 more in the near future. And basically, it will put a lot of sources of light in the atmosphere. Sources of light because they reflect sunlight. And so that has a damaging impact on all of astronomy. Significant impact on, for example, the Large Synoptic Survey Telescope, LSST, because basically you will see, even if they paint those satellites black, which they said that they might do as a matter of courtesy to the astronomers, to the scientists, with the LSST you could still see them quite easily, and whenever such a satellite passes the field of view, it contaminates the image quite severely. And Tony Tyson, who is leading the Large Synoptic Survey Telescope, is very worried about that. So they tried to establish a program by which they will basically avoid those satellites whenever they come in, and they did it for 12,000, the plan that is approved as of now. But now SpaceX is asking for another 30,000, the government, and there are no laws in space, so you can do whatever you want in space. There are no restrictions. So that's a big dark cloud, or I should say bright sources of light hanging over the astronomy community right now. And
will we see them with the naked eye or no?
They are, they are putting them far enough so that you can't see them. But some of them you can still see. But eventually, I mean, most of them will be far away, so that with the naked eye you won't see them, but with telescopes you would easily see them. And right now they were actually not painted black even, they were just reflected, they are easily visible. Once they paint them black and put them farther away, you won't see them. But it's a serious matter for the future of astronomy, and of course if they cover the atmosphere with those, if there are more than 30,000 in the, because this is just the beginning of the process. I mean, the goal of these industries is to allow internet to be accessible anywhere on the globe. And so they say, you know, it's great for remote places in Africa, in India, and anywhere. You would get direct access, and you know, and actually Elon Musk was bragging that he was using Starlink on his, you know, iPhone. So it definitely is a way to make a lot of profit for these industries, and since there is
on his iPhone.
Yeah, through some application.
He has a better iPhone than the rest of us. Mine won't even reach AT&T, and he's talking to space.
Well, they have special access to Starlink from the company, but the point of the matter is that the question is whether there is a conflict between science and the private sector or between profit and non-profit organizations.
And if a few of them break apart and fragment, then you can quickly get to the point where you're never going to get rid of that
the debris. That's a separate matter. How to clean the atmosphere, the satellites. Yeah, but even if one imagines that they will survive for a long time, the question is how to deal with it for astronomy. And you know, at radio frequencies, there were restrictions put on transmission because of radio astronomy. There is none at the moment on satellites. So this will definitely be featured at the decadal survey of the astronomy community, and also in a couple of weeks there is a committee that will look into that I will participate in. So it's really a serious matter. Anyway, just so that people know that maybe we will eventually need to put our observatories on the moon, not because of
angular resolution.
That's right. Okay, so we have 2 speakers today. 3.
Yeah, let me mention, following up on that, because we have 3 speakers, let's try to keep the questions during the talks to a minimum. After the talks, and then the period after the colloquium ends, those will be time to discuss with the speakers any questions or concerns. So our first speaker is from University of Michigan. He's a postdoctoral fellow there. His name's Pengyu. He's going to be talking to us about Penrose and equality.
Thank you for the introduction and a great opportunity to speak here. Okay, so the title of my talk is Penrose inequality. So I will first discuss
No, the other way around.
Sorry.
yeah. So first I will discuss some history on the works of black holes. Then I will introduce how Penrose get his inequality, and the third part is some proofs of some versions of Penrose inequality. Okay. So first, in 1950s, within a month, Einstein get his theory done. So first paper is in November 1st, and he get the field equation which is equal to the energy momentum tensor, and 3 weeks later he get the right field equation, and which is the way we use today. And soon after he get his equation, Schwarzschild find the first you could say black hole solutions. So this is Schwarzschild's solution. So which looks like this, and from this formulation, you can see there seems 2 singularities in this metric. One is I is equal to 0 and I is equal to 2m. But the understanding of this metric changed slowly. So in 1924, Egerton discovered a coordinate transformation, and actually under this coordinate transformation, you can write down the metric like the following, and somehow you don't see there's no singularity at I is equal to 2m. So, but he didn't notice it. And in 1958, Finkelstein rediscovered this transformation. And you can see in his paper, he discovered this very interesting phenomenon, which is the causal infractions can cause across the membrane. I is equal to 2m, but only in one direction. Actually, he already, this is what he is saying is that this is an event horizon. And finally, Kraskov and Shinkers, they find the coordinate system which cover the maximal analytic extension of Schwarzschild metric. So this is the formula, but we can look at this picture. So so every point in this picture represents a sphere of radius r, and this is the black hole region, and I is equal to 2m is the event horizon. Okay, so the Schwarzschild solution is a static solution, and at that moment, you don't know whether black hole can form dynamically, right? So it's in 1979, Oppenheimer Schneider studied the first work of relativistic gravitational collapse. And particularly, they found the star collapse in a finite time. And they noticed after the star is collapsed, the observer on the surface of the star cannot send signature to the outside. And this gives the intuition, leads to the concept of future event horizon and black hole. So, up to now, other works on black holes, they are either done including special symmetries, like spherical symmetry or asymmetry, and also or either some perturbations. It's later Penrose introduced more general methods to study space-time without any symmetry or not perturbation. Without any symmetry. So here, Penrose introduced the idea of the conformal compactification. So in this way, he defined the non-infinite. So this is the Penrose diagram of the structure of the Minkowski space. And this is the Penrose diagram of the structured metric. Okay, so this is in 1964, and in 1965, Penrose introduced another very important notation, which is called a closed trap surface. And inside the black hole of inside structured black hole, any surface inside the black hole which decrease its area in both future directions. So this actually is a trap surface. And with this concept, he proved the incomplicit theory, which he basically says under certain physical conditions, the existence of a closed trap surface implies the space-time is not future nor geodesic complete. Okay, so this is some basic knowledge and on black holes. So now let's turn to the Penrose inequality, which is the topic of this talk. So in 1960s, Einstein studied the linearized solution of Einstein's equation, and he discovered the gravitational wave. But this work is a linear theory, and even Einstein himself doubted whether the result can be trusted. In 1962, Bondi considered the general antisymmetric solution of the Einstein equation, and he is doing for the nonlinear theory. And for such solutions, he defined several important quantities. One is the Bondi mass, and the other is the Bondi-News formula, and they are related by this Bondi mass-Luce formula. So the derivative of the Bondi mass is related to the news, and you can see this quantity is unnegative. So by this formula, he get his most significant result. So the mass of so this is the future non-infinite, and in this direction, in the future direction, the Bondi mass can only decrease. So so this is what we have on the non-infinite. And on the event horizon, we also have a monotonicity quantity. So this is related to black hole entropy. So in 1970s, Chris Duro, he introduced irreducible mass and reversible and irreversible transformation. And this from this terminology, it reminds you of thermodynamics, right? And he discovered the irreducible mass can only increase in the process. Then in 1971, Hawking found a very general proof of the following fact: the event horizon area cannot decrease in any process. So, and for Kerr and Kerr-Newman black holes, the area horizon and the irreducible mass, they are related by this very simple equation. And motivated by this, Rothenstein, he conjectured the black hole should have a well-defined entropy, and which is proportional to the black hole event horizon. And it's confirmed by Hawking. He showed the quantum mechanical effects can, can cause radiation, so which is the Hawking radiation. And he found the constant of proportional should be equal to a quarter. Okay, so now apply this, apply the bounding mass loose formula and the and the black hole entropy. So we can apply this to the gravitational collapsing. So this is a general picture of gravitational collapsing. So in falling matters, they form a black hole. So inside the black hole, first you can find a surface which is called a moderate charge surface. So it's like if you go inside a little bit, the surface became charged. So this is called moderate charge. And the first thing is you have the area of the moderate charge surface is less than the area of the intersection of the event horizon. And then on the event horizon, if you go to the future, since the area, the event horizon area would not decrease. So you would have the area of this section will not decrease in this direction, and it will tend to a limit at a space like infinite. And here, actually, we apply, implicitly, we apply the weaker cosmic censorship hypothesis, because the existence of the space like infinite depends on we have a complete future non-infinite, which means we don't have negative singularities. So here, we already applied a very strong conjecture, which is we don't know. We don't know how to prove it. And at the space like infinite, we have the following inequality holds. This also we apply so this is the limit of the body mass at space like infinite. And this holds because we assume other conjecture is like in the end of gravitational collapse, we either form a curved black hole or curved Newman black hole. And this formula, this relation is true for curved or curved Newman black hole. And then we can go backward. And if we go backward, the bounding mass would increase or not decrease. Okay, so we get this chain of inequalities, and the area of the material charge surface and the total mass of the black hole. So this is less or equal than this. This is the Penrose inequality. Okay, so let's go to the third part. Okay, so so the heuristic argument by Penrose, he implies he make use of very very difficult conjectures. Here is the weaker cosmic censorship, and here is the final state of black hole. And so this became very difficult to verify his argument. So from then on, people try to find a direct proof of Penrose inequality to prove this is less or equal than this directly. And so the first, and this is not the first, but a very big breakthrough is achieved by Huiskin and Yeoman and by Braatz in 2001, and they proved a very general case, which is called the Riemannian-Penrose inequality. So this is related to the general Penrose inequality in the following case. So if you can see the space type which has a tie symmetric, and you pick the space-like slice, which is the surface of the symmetry. The surface of the symmetry, and on the surface of the symmetry, the event horizon would be minimal surface, and and the unnegative scalar curvature condition, which actually is implied by the energy condition. And this is the so this is equivalent to the Penrose inequality we just read before. So the Hawking the mass is greater than this this quantity involves the area of the horizon. Okay, so the proof makes use of inverse mean curvature flow. So this inverse mean curvature flow is proposed before by Grosch. He found that the Hawking mass is monotone, non-decreasing around this flow. But you have difficulty to construct this kind of flow because, yeah, okay. So Whiskey and Inman they construct this weakly inverse mean curvature flow, and they show the Hawking mass is still monotone, non-decreasing. So actually, you can flow the minimal surface, the event horizon, all the way to infinite. And the Hawking mass is monotone, non-decreasing, so you can relate it to the Hawking mass of the minimal, the event horizon, and the ADM mass at infinite. Okay. And this result is for so this result is for only one component of the event horizon. If you have a several black hole, so if you have several minimal surface, what he can show is any the surface, the area of any minimal surface is less or equal to 60 pi m squared. Okay, and the brain he used another method, and actually he can show a stronger how to say, he can show the total surface area of the minimal surface. If we add them together, they are less or equal than 60 pi m squared. So this is not only one connected component, it's the area, the sum of all the area. Okay, so he make use of other method. He construct a family of metric on the manifold, and by conformal deformation, and he can show the area of the area of the horizon of this surface, of this metric. The area of the horizon there are fixed, but the ADMS decrease. And in the end, you will get a threshold metric, which is the inequality actually is equality. So it's like the surface, the area of the horizon is fixed, but the ADMS decrease. And in the end, they match. So you get you prove this inequality. Like this. Okay.
So maybe you already mentioned, but what is the value of the ADM mass?
This is defined by three physicists, which is the integration of the derivative of the metric at the infinite. So you can write down an integration to define this quantity.
Okay, and what is? Do you remember what is the? I mean, I want to know because it seems like it's very important boundary for the growth of Hawking mass, right?
Oh, it's hard.
What number is it? Yes. Okay.
Okay, so this is the work by Whiskey and Inman and Braatz. So they proved this Riemannian Penrose inequality. So there are other versions of Penrose inequality. So here, you can consider the Penrose inequality on a space-like hypersurface. You can also consider it on a non-hypersurface. So here, for example, if C bar is a non-hypersurface, you can compare the area of the marginal charge surface with the bounding mass at non-infinite, right? So before you compare the area of the marginal surface with the ADM mass here, but you can also compare the area of the marginal charge surface with the bounding mass here. And you can the conjecture is the following. So for bounding mass, you have also the Penrose inequality pose. Okay, so I should remark, actually, this does not follow from the Penrose inequality we said before, because around this direction, the bounding mass would increase. So even the mass, this is less or equal than the ADMS here, it does not imply this is less than the boundary mass here, because so this is actually stronger than the Riemannian Penrose integral you could see. Okay, so this inequality, we don't know how to prove it in general, and we make the following assumption. So we consider a null-hype surface, and we consider a neighborhood of this null-hype surface, and we assume this neighborhood of this null-hype surface is a perturbation of structural metric. And we want, for this space type, we want to show the null Penrose inequality. Okay, so how to do it? So we can, for example, we can imagine the similar idea of Huisken and Illman, and we can try to construct a flow or variation from the marginal Trump surface all the way to non-infinite. And if we can show the Hawking mass is monotone non-decreasing, we might how to say, compare the Hawking mass at this point and the boundary mass at this point. Okay. So this is done by Salter, and he constructed two kinds of variation, and for these two kinds of variation, the Hawking mass, they are all monotone non-decreasing. The first is called the constant non-expansion variation. The second is called the constant mass aspect function variation. And I cannot give the definition of these two variation, but they are all related to the geometry of this variation. So they are related to the geometry of the surface, and they are also related to the frame on the surface, the null frame, L and L1. Okay. So, yeah. So this the first variation actually is an analog of the inverse mean curvature variation, but the second one it involves such very strange function. So why is called the mass aspect function? So the first reason is if you take the integration of this surface of this function, it will give you the Hawking mass. This mass aspect function was defined first by Christodoulou in 1991, and then it's used in the proof of stability of Minkowski. So this function does not come out from nowhere. Okay, so by Salter's construction, we have the following. Since the Hawking mass is the derivative of the Hawking mass is unactive, so we have this inequality. The initial Hawking mass is less or equal than the limit of the Hawking mass. Okay. So the next thing we need to show is there any relation between these two quantities? If this is equal to the boundary mass, so we are done. But unfortunately, it's not the case. So this is two variations. So the first variation, you can see at now infinite, the variation is not round. It has this shape, which is not round. So since it's not round, this limit does not have any meaning, physical meaning. And the second case, if the variation is round at infinite, so this variation actually defines a reference frame, and this limit is the boundary energy measured with respect to this reference frame. So if the variation is round at infinite, then this limit does have some physical meaning. Okay, so so the question is, does the variation constructed by Salter is round at infinite? But somehow we cannot expect it. So in general, it is not true. So on one null-hype surface, and if you start from a marginal Trump surface and you construct this variation might not be round at infinite. So this is the problem, and how to solve this problem? So we consider the following idea. So here is the null-hype surface, and sigma 0 is the marginal Trump surface, and we construct a variation. And we assume this formation is not round at infinite. So what we try to do is we try to find another imaginary charge surface nearby, and consider this new null-half surface, and we construct a formation on this new null-half surface, and we hope by choosing another imaginary charge surface, the new formation would be round at infinite. Okay, so this is the idea. So basically, there's the approach might not how to say, give us anything on the original null-half surface, but we can find another null-half surface such that the approach works. Okay. So this is what I did. So actually, you didn't find only one. Actually, you find a 4-parameter family of imaginary charge surface such that the formation from this family is round at infinite. So an immediate corollary of this is since the formation is round, they define a reference frame. So you can, by the monotonicity of the Hawking mass, you can compare the Hawking mass of the initial null-half surface, imaginary charge surface with this boundary energy. Okay, but this is boundary energy. It's not the boundary mass. So there's still a gap between the boundary energy and the boundary gap. So what we can show is actually in this 4-parameter family, you can pick a 1-parameter family such that the formation is not only defines a reference frame, it defines a center of mass frame. Actually, you can use because you see we have a 4-parameter family, and you can kill you can kill the angular momentum in this 4-parameter family. So there's only 1 parameter is left. And for this 1-parameter family, what you can show is the boundary mass, the boundary energy actually is the boundary mass. And moreover, actually, you can choose a imaginary charge surface such that it has the same area with the initial one. This initial one is the one which the reference frame does not define. The formation does not define reference frame at infinite. So, yeah, okay. So this is my theory. Yeah. End of my talk.
Questions for Pengyu?
Did the assumption that the neighborhood of C is a perturbation of Schwarzschild enter into Sauter's definition of the foliation, or does it only enter into your proof?
No, it enters to the existence of the foliation, but the definition is general. The definition of the foliation is general, but to make sure the foliation exists, we need additional assumptions.
Does the assumption play a crucial role in your construction of the special marginally trapped surfaces?
The construction of imaginary charge surface does not how to say make use of. It's not how to say the perturbation of structured metric plays a role at infinite actually. So, but in order to find the nearby imaginary charge surface, you don't need to assume the metric is a perturbation. Yeah, to find the
Do you assume the null energy condition?
Which condition?
The null energy condition.
I forgot to see. This is vacuum. Yeah.
Oh, I see.
Yeah, it's vacuum. So, yeah.
So how much the derivation would change if you actually relax the assumption of having like a 3D flat, like a 3-dimensional to be flat asymptotically? I think that in one of the slides you showed that the conjecture that you had was like for asymptotically flat.
Yes.
But do you have any idea? Because then the curvature would also get into the.
This is because we consider isolated system, and for isolated system, it's natural to assume as asymptotically flat. To release this condition, I didn't see any work release this condition. Most of assume asymptotically flat.
do you expect to see any sort of curvature impact in your upper bounds? Or?
Yes, the scalar curvature satisfies a lower bound condition. So the scalar curvature, I think has a lower bound, which is like this is the scalar curvature. I think it's this, so it's greater or equal than it's like a 1 over r square. Cube or square? Because if you take oh yes. Sorry, because yes. Yeah, the curvature. Yeah. So you do have a condition on the scalar curvature, because if you don't have this, even the ADM mass is not defined as far as I know. Right? Because you have this integration of you have this definition of ADM mass, and which is the integration on the large sphere. And if you use the integration by part, then you get the integration inside the sphere. And what you get is the scalar curvature, integration of the scalar curvature. If the scalar curvature does not have this bound, the ADM mass is not defined.
In the interest of time, we'll move on to the next speaker, and further questions can be directed at you after the colloquium. So let's thank him one more time.
So our next speaker is going to be Jim Braatz. Jim is an astronomer at the National Radio Astronomy Observatory. He's been doing radio astronomy for a while. He's an expert in both single dish and interferometric and VLBI observations. I work primarily with AGN and supermassive black holes and megamasers, and he's the PI of the Megamaser Cosmology Project, which is something he's going to be telling us about today. Take it away, Jim.
Good. Thank you, Dom. So I'm really happy to have a chance to tell you about this observational program that I've been working on for some years. It involves several people right here at Harvard, including Dom, who's, you're going to see his fingers are kind of throughout the talk that I'm going to give today, with a lot of the excellent work that he's been doing over the past few years, as well as Mark Reed, who is not here today, but he was one of the people that helped me to originate this project. So I'm going to be talking about masers that are orbiting the supermassive black holes around AGNs. Not so interested today in the maser properties themselves, but I'm interested in using them as point source tracers. So we can use VLBI observations to measure the relative positions of masers to within a few tens of micro arc seconds, and we can measure the line of sight velocities of individual masers to about 1 kilometer per second. And this makes them extremely valuable astrometric tools. And so I'll talk about a couple of the applications for that. The one I'm going to focus on is that has kind of motivated much of the project is using these masers to measure distances to galaxies, and so we can get a Hubble constant. But there are lots of other applications. I'll mention a little bit about using the masers to measure the masses of the black holes. These masers are found within the sphere of influence of the black hole, and so we get, as you'll see, very precise masses. I used to say the most precise masses outside of the Milky Way galaxy, but the M87 result now rivals that, so I have to tone my language down a little bit, but I think it's still fair to say that it's that these set kind of a gold standard for mass measurements. They also provide essentially the only way to map molecular gas on subparsec scales in AGNs directly, and so you can use these masers to learn about things like orientation of accretion disks on these scales. You can learn about the physical conditions of molecular gas on subparsec scales. And then we've kind of come up more recently with some kind of special little applications, including measuring peculiar motions of the supermassive black hole within the AGNs. I won't get a chance to talk about that one. Dom actually is a leader in that particular one, and I'll be around this week though if anyone wants to talk.
Which telescopes are shown?
I'm sorry?
Which telescopes?
So this is actually a VLBA antenna, which the VLBA is primary in our VLBI observations. This is the Green Bank telescope, which I'll mention gets used quite often in our project, both for finding the masers and also for providing the sensitivity that we need for our VLBI observations. And then this is the Effelsberg telescope, the 100-meter telescope in Germany, which Whenever we can, we include the Effelsberg and the VLA as well, because these masers are faint, and we need basically all of the telescopes we can find that work at 22 gigahertz to make these observations work. Okay, so the story for cosmology begins essentially where free-flowing radiation in the universe begins, and that's with the picture of the baby picture of the universe from the CMB. So with CMB observations, you can calibrate the lambda CDM model for cosmology and make a prediction. And the prediction is a very precise one for what the Hubble constant is. So this is the predicted Hubble constant, 67.27 to better than 1%. With this prediction, the idea then is to go out and make measurements of the Hubble constant, and that provides a powerful test of the lambda CDM model for cosmology. And so I would say the highest profile measurement of the Hubble constant in the local universe is based on very traditional methods of using standard candles. So it starts with Cepheid variables, which are a standard candle that can be observed out to about 30 megaparsecs, not quite far enough that you need in order to get into the Hubble flow. So they need to be connected to type 1a supernovae. But to calibrate the Cepheids, you can use local geometric anchors, which include either direct parallaxes for Milky Way Cepheids, or detached eclipsing binaries in the Large Magellanic Cloud, or the Maser and NGC 4258. I'll say a little bit more about that later. The result of the direct measurement is 74 plus or minus 1.4. And so this is 4.4 sigma discrepant with the prediction from the lambda CDM model.
There will be a physics colloquium by Adam Rees Monday.
Awesome.
If anyone wants to hear more.
Oh, Adam gives a great talk. So, if you read the Washington Post this week, what you found out is that scientists are baffled. We are a baffleable bunch of people. And so we don't know what's up with the universe. If you actually took the time to read what was in this article, what we really are is very excited by this discrepancy, because it offers the opportunity for us to understand something new about the universe that we don't know. But what we also are, from Joe Dunkley, who's studies the CMB, a professor at Princeton, is skeptical. The measurement based on standard candles historically have had unrecognized systematic errors, and so we need to be skeptical of the observations and our understanding of the uncertainties in those observations. And so what we like to do then is have multiple methods to measure the Hubble constant using independent means to confirm these rather extraordinary claims. So that's what I'm going to tell you about this megamaser cosmology project. The goal of that is to use these masers to measure the distances to galaxies directly. We don't use a distance ladder. It's a one-step measurement. We don't use any sort of standard candles. It's an angular diameter distance based on a geometry. It requires a few different types of observations. We need to find the right type of maser systems. We need to image them with the LBI, measure some accelerations, which I'll describe, and then model these maser systems to get a distance. So kind of to set the stage for what I'll be describing later is just a little cartoon here, not real data yet. But this is kind of a representation of what a time series of spectra might look like if we were looking at a maser system, and just a cartoon model of what we're looking at. So it's an edge-on accretion disk, the black hole in the center. Masers are detected in 3 special locations, directly along the line of sight to the black hole, and then on the tangential line, we call that the midline, at the edges of the disk. So we can measure rotation curves by looking at these maser components, which are either rotating directly toward or away from us. In the time series, what we expect to see when we look at these spots, which we will call the systemic maser spots, is that maser lines will appear on the blue edge and drift redward with time, and that redward drift that we're seeing is a change in velocity with time, is the centripetal acceleration of these individual maser components as they orbit around the black hole in the center. So that acceleration is critical in measuring the distance, as I'll show you later. In fact, it's in most cases it's the critical step that sets our uncertainties. The maser features in the red and the blue shifted lines, they don't actually drift, not because they're not accelerating, obviously, but because that acceleration is in the plane of the sky, so we don't measure that component. We measure essentially fixed lines there. They do vary, though. Masers are highly variable. So just in the simplest geometry, a distance is just the linear size of the disk divided by the angular size. We just write simply the centripetal acceleration, v squared over r. And so we can get a distance from three observables: the rotation velocity, this acceleration, which we measure from the drift, and the angular size. So if the masers all came from a single ring, those equations would apply. In fact, they come throughout a range of radii in the disk, and so we have to apply a more sophisticated modeling. So this is just a conceptual representation. Okay, first step, we need to find masers that are appropriate. And so we've used the Green Bank telescope, which is by far the most sensitive single dish telescope and the most efficient way to search for these masers. Unfortunately, these searches are extremely inefficient. We detect about 3% of the galaxies that we survey, which are mainly Seyfert-2 galaxies in the kind of a distance range of roughly 50 to a couple hundred megaparsecs. The reason that they're inefficient is because these masers are optimally beamed toward our line of sight if they're perfectly edge on, and so it's very geometry dependent, and we don't know a priori what those geometries are. So we've surveyed several thousand galaxies in order to find about 160 known megamaser systems now, and about a third of those actually come from disks that have this very characteristic spectral profile with three distinct groups of maser features. This is just kind of a rogues gallery of what these maser disks look like. And so in each case, you can see three distinct maser features. The typical rotation velocities can be read right off of any individual spectrum, and they range up to about roughly 1,000 kilometers per second. More typically, a rotation velocity is about 500 kilometers per second. For any of these systems, we can get a black hole mass precisely with just a VLBI map. And so that's relatively easy. It's still a lot of work, but we can get a VLBI map for essentially any one of the masers that I've shown here, and we have now something like 23 VLBI determined black hole masses. But to get a distance, we need something even more than that, and that is we need the systemic masers to be bright and to have essentially a rich maser spectrum that allows us to model the maser systems well. And so these highlighted in red spectra are the galaxies that we focused on for trying to measure distances to those galaxies.
No binaries.
No binaries, no. Not black hole binaries anyway. There's one galaxy that we're looking at that seems to have a peculiar motion that we're still trying to understand. I can tell you more about that. So this galaxy here is one that Dom has been working on, and we have a paper coming out very soon with a precise measurement to that one.
If only the middle is very visible, the middle spike, does that mean, is that just geometry?
So so the middle spike has the opportunity to amplify continuum emission from the black hole region directly, whereas the high velocity regions don't have that opportunity. These have to be self-amplified. That can be amplifying continuum. So in some cases, it may be that there is a continuum that is providing more seed emission to the maser, but I think in general, we do see a couple of cases where the high velocity lines are brighter, and I think it's probably more dependent on geometry. Yeah.
It's the column density of material that has zero velocity gradient.
That's right. So you have to have a line of sight velocity coherence in order to maximize that maser gain. Right. So this is just a picture now of the VLBI image for some of these galaxies. When we're measuring a distance to the galaxy, we typically need to get multiple VLBI tracks on each source. So each one of these pictures represents 50 or more hours of VLBI time using all of these big dishes. It's a lot of work. Typically, a study of one galaxy is about half of a PhD thesis. And so what you see here is that the masers are color-coded in the usual way, red and blue, rotating away from us and toward us, and the green maser spots are the ones on the front side of the black hole on the accretion disk. Typical sizes for the maser disks are a few tenths of a parsec. Typical angular sizes for the maser disks are about a milli-arcsecond. And excuse me, I mentioned earlier that we can get relative positions of maser spots to much smaller than the beam size because we can, since the masers are unresolved, we can measure their positions by centroiding. Excuse me. So we do see slight warps in a couple of the cases, but in general they're fairly flat. Excuse me, got a tickle. So here's a case of UGC 3789, which the GBT spectrum shown here, the VLBI map. This is a rotation curve where you can see that the high velocity features are very well fit with a Keplerian rotation profile. If you look closely, you see a little kink in the representation of the systemic maser features, and that's because the masers there are coming from a range of radial distance from the central black hole. On the right is a representation of the acceleration. Oh, thank you very much. On the right is a representation of the acceleration as measured by picking individual peaks of maser components in the systemic part of the spectrum and plotting those peaks over time. And so where you see positive going slopes, that's representing a maser feature that's drifting redward with time. So that slope is the acceleration that we need to measure that distance ultimately. Since that's critical to the process, I'll show that to you in several different ways. Here's a dynamic spectrum showing the blue, the red, and the systemic features. So you can see the flat lines representing that the blue and red features do not drift with time, but the positive going slope here shows how the systemic features are drifting. And we can even look at a little animation of the systemic features where now you can see if you follow individual peaks, you can see that they drift to the red in these real data now sequence of spectra. What you also see is that the maser lines are, are variable and are blended. And so to measure these accelerations, we have to apply a Gaussian fitting code that fits each of these lines individually, and the blending and the signal to noise are essential features in maximizing that. So we need sensitive spectra, and we need maser spectra that have a lot of distinct individual features.
How do you know it's the same cloud? You don't
That each individual line is the same cloud? Well, I think, in some cases, like over here, you can actually trace this one individual peak drifting. There can be maser features that appear and disappear over the monitoring period, and so the fitting code that we use has the ability to fit down to 0 amplitudes. In general, the maser features do persist. If I show you the dynamic spectrum, typical maser features do persist over a couple of years. So here's a time in days. Each one of these bands is about a year. So they do persist over a couple of years, but you can see that there are flares that come and go. So we need to be careful about how we treat those lines. So once we've got now from VLBI the position of each maser spot, from monitoring the acceleration of each maser spot, we can model the disk, and we model the disk with a warped disk. This is kind of a representation. The black line is showing our line of sight, the red and the blue and the green maser spots. This is a real model fit for UGC 3789. for each maser spot, we fit the radial distance and the azimuthal angle as fitted parameters, but we have 4 inputs for each maser spot, x, y, z, and a. And then we have a few global parameters. Most of those we're just marginalizing over the position of the black hole. The warp parameters are not particularly interesting to us, but the mass of the black hole and the distance to the galaxy are the parameters we're interested in. So we actually use now 2 different codes using the same, essentially the same parameterization. One developed by Mark Reed, the other developed here by Dom, and we have convergence in these 2 codes. We're quite happy about that. The code that Dom has developed has the advantage of incorporating some error floors that we were using in the old code, kind of a tunable parameter. We're trying to remove all of the tunable parameters from our model fits, and also a kind of a quicker convergence time. This code takes a couple of weeks to run on a typical system, and the new code can be fit in a day. So once we've done this model fitting, here are the 4 best galaxies that we've done so far. And our result to date is 74 plus or minus about 4%, based on these 4 galaxies only. So we have another 5 galaxies with the data in hand that we will fit. These are the 4 best ones though, and so I think when we fold in the additional 5, we'll bump our total uncertainty certainly below 4%. I don't know if we'll get quite to 3%, but we'll soon find out about that. But what you can see is that our number is coming up very close to the measurement from the standard candles value.
So
What's the biggest source of error?
I think it's the measurement of the accelerations in almost all cases. So there are 1 or 2 galaxies where our VLBI data aren't quite as sensitive as we'd like them to be, but it's the accelerations that really limit our measurements right now.
So how do you take the average of them? I mean, because some of them are just very similar to CMB inferred H naught, like a 66, but some of them are just very high, like a 81. So I think yes, my question would be that is there any evidence that some of them could be even more like a precise your measurement, or you just put them like statistically and just average them to get something which is in between?
So for this, I've only done a weighted average of these four measurements. We think that the measurements are independent. There aren't really any. There's no reason that there should be correlation. We're using the same model, of course, but.
But then why there are so much varied?
I think there is certainly variance here, but we're only looking at 4 numbers right now. So I guess I could certainly run a test and see if these are consistent to apply that weighted average, but I think they are.
Chi-squared of these 4 is about 1. Yeah, so these are perfectly statistically consistent with measuring the same value.
Are these in the Hubble flow? Yeah. What are the distances?
Yeah, so the distance to 3789 is about 50 megaparsecs, so it's just on the edge of the Hubble flow. We do incorporate a peculiar velocity uncertainty in that, so it's folded into this measurement. And then 6264 is the most distant one, and I think, let's see, that one's about 150 megaparsecs, so that one's well into the Hubble flow. And the other 2 are intermediate. So just to be provocative, I pulled up 3 values from completely independent measurements. So this is the Adam Rees-Shoes measurement. This is a measurement of H0 from gravitational lenses from the Holy Cow project. This is the measurement that I told you today. And if I just take a weighted mean of those, I come up with a Hubble constant of 74.5 plus or minus 1. And the Planck value over there. So right now we're at, just to be provocative again, a 5.6 sigma difference between these 2, which I think is compelling. And I think we're on the brink of no longer calling this tension in the Hubble constant, but rather calling this the problem with the Hubble constant. And so I think we're kind of at an exciting time right now. I will mention that a more recent observation also by Wendy Friedman's group that uses the red giant branch to then calibrate type 1a supernovae, so not entirely independent of that method, but they did come up with a value of 69.8 plus or minus 2.5%. But anyway, I think this is now getting to be really quite an interesting problem.
The problem is really that none of the theoretical attempts to explain it make any sense.
Yeah.
So I mean, it may be excluded theoretically.
Yeah. Well, as you know, I think you're one of these numbers here. So, so the question is, what kind of new physics can explain that sort of discrepancy? And I don't have time to go into that in detail, but basically looking at things that can modify pressure terms early in the universe, looking at possibly new types of relativistic particles, non-zero curvature. So there are a lot of ideas. What we know it's not is a local void. This is often a question that comes up. If it were a local void, then we would actually see that signal already, and we are measuring galaxies out far enough into the Hubble flow to discount that. The local variance in the Hubble constant from voids can only contribute kind of a few tenths of a % variance in the measurements. Okay. Although that is compelling, I think the goal of the observational community is to try to approach 1% measurements using multiple independent techniques. And we don't have the hardware right now to do that at 22 gigahertz with our current telescopes, but on the horizon is the next generation DLA. So this is a telescope for the next decade that will improve our sensitivity at 22 gigahertz by about an order of magnitude, and I think this would enable us to approach a 1% solution with maser observations. Just very quickly, I want to mention a couple of other applications of these masers. So I told you that we can measure precise black hole masses. The types of galaxies that we're observing are relatively nearby Seyfert 2 galaxies, and they all kind of have black hole masses that cluster around 10 to the 7 solar masses. It's quite different than the black hole masses measured optically, which tend to come in early type galaxies. And so these maser measurements do begin to allow us to fill in some previously blank spaces in scaling relations. So this is the M sigma plot. And what we're finding is that masses determined by the maser method tend to fall below the M sigma correlation defined by elliptical galaxies. And that could be representing either that the masers are in a special transition phase of their evolution, or that there's some other sort of bias, or that we're just actually beginning to see some evolution for the galaxy types as they proceed along the M sigma curve. And then just in my last second, I want to mention all of this discussion has been on 22 gigahertz masers, 1 centimeter wavelength. The water molecule actually has a host of transitions that can maze, and most of them fall in the submillimeter part of the spectrum. And so we have been interested in using ALMA lately to see if we can start to observe some of these submillimeter transitions to kind of complement what we've been doing with the 22 gigahertz line. And we kind of are just getting started in this, but our approach has been to begin by targeting known maser disk galaxies in the other maser transition lines. The 183 gigahertz line is one that's predicted to be quite strong. And here is a comparison for 4 maser disk galaxies where the red line shows the 22 gigahertz emission, the black line shows the 183 gigahertz emission. We've targeted 20 galaxies, we detected 13 of them. In this one, we see the full range of maser features, the high velocity lines as well as the systemic. And so we certainly are going to have an eye toward spectral line VLBI with submillimeter masers in the future. Okay, and I think I'm going to skip those last couple and just finish with my summary. So these sensitive VLBI observations enable some unique looks into cosmology and into masses of supermassive black holes, galactic evolution, and AGN physics. Here's our most recent measurement for the Hubble constant, 74 plus or minus 3.1. MGVLA is in our future and is going to help us get to a 1% solution. And we're happy to have Alma now to look at some millimeter masers. Thank you.
All right, time for maybe one question for Jim for a little while. Go ahead, Avi.
So cosmology is a bit boring. It's about one number or several numbers, but you actually have much more data than that. And the interesting question is, we do see a circumnuclear disk around Sagittarius A star that made stars in the disk. And we know that when massive stars form, they often maze, right? We see masers. So are these clumps just stars formed next to the black hole in those distant galaxies? A very simple model, but do you have data to support it?
I don't think they are stars. There's a great. I mean, there's a lot of. So the word is failing me. There's a lot of the shear motion of the accretion disk. I think is not very conducive to star formation. Kind of at these distances, the gas is moving 500 kilometers per second.
If it's cold enough, the Q parameter is one. Tumor criterion.
Yeah.
I think these are unstable to fragmentation.
Yeah, but even the ones you're talking about in the Milky Way, there's not motion kind of at that. These are, you know, like in the circumnuclear ring, that's slow rotating gas, a couple hundred kilometers per second. I can't rule it out, I guess I would say. If it were actually from stars, I guess we would have to think about what causes the variability. The picture that we have in our mind is that it forms from filaments of the gas within the accretion disk, and these filaments can kind of bend and wiggle over time and as the gas rotates around. And so the variability that we're seeing comes from a filament of gas changing its line of sight.
Apart from variability, these are megamasers. Doesn't it mean that they are much stronger than ordinary stellar masers?
They're stronger by orders of magnitude.
Orders of magnitude.
Yeah. So, but you could still have line of sight. You know, you could have 2 masers along a line of sight with a background source pumping a maser into a foreground source that then gets amplified again. I think there are ways to get around that a little bit, but yeah, but you're right. These are a different beast.
All right, just in the interest of time, let's thank Jim again and move on to our next speaker.
Fingers.
Oh, yeah. Supermassive star. Usually you just have a huge star. I see, so it's a mega star.
Yeah, mega star. And I think it's a very interesting question.
Well, so I think, let's give it a minute, it's still thinking. In those cases, it's using the fragments. I would need to think let me know. Because I've been thinking about it. Okay, well, I haven't thought about it. I think one of the things I do think about, and this is something I should back in Berlin.
It was crazy because it's the 30th anniversary of Berlin.
But don't have any offset from the midline. Anyway, there's a couple of
whether one can use the
what would it take? These mega stars are called back from radio.
we have to debrief. I mean, all stars about fusion,
right.
So computers are
I think, yeah, if we can find, if it's reasonable to argue that the spatial scale can be whatever log of a million is bigger. It's basically what you need. It's about an order of magnitude, maybe a little more, maybe 20 or something. Right, you can be pretty big, but maybe achievable.
Within a few times.
So the question is, what would be the test?
Right. This is what I need to think about. The very
One small technical delay, guys. Give us 30 seconds.
And then the biggest disk that we see.
Or maybe not.
Some lasers that are a little bit farther out. Right, this is sort of thing. Can we get close enough to do this?
Yes, it's just
One of these,
once you are massive twice like this. That's more thing they try to work in.
Well, yeah, if you get
These are corners.
So we can get some. Let's say 1,000 or 10,000 like because it's very good. And you ask how many velocity you can see it.
Yeah, we can probably choose the maze
And what would be the spectrum if there is a lot? You know, so for example, massive stars, they will come from. So they produce very signal.
Good.
So if you end up with three signal, you get what I mean. So that's exactly
Water maze is more like 1,000. Last G is
how much starlight there is. Maybe not so much. Just check because each of them is so apart.
Froze my computer.
Each of them is
that's what I mean. If it's 10,000,
and then you're like, that's a million. So
features,
right? And you can offset it.
Give
me just a second.
So did you do that? Okay.
Because most stars are much less than
Much less than that, right?
So only 1%.
So that's
So that would be interesting.
Yeah,
And it's a definite prediction. You see it now?
Yeah, people are taking this. I look at the HSC spectrum, so I think super
It's just trying to saying the full screen. I think all the variability we see is probably related to this change in
that would be super amazing. That would really, that's a good idea. That would be a crazy.
Yeah, that
would be pretty bona fide. That would be hard to fake.
And then you can consider
or you can well, depending on how some ridiculous number, right? Yeah, and then we can just forget it. One thing at a time. Let's first see if that's actually the cause. That would be super.
Fortunately, it shields my laptop.
What is this?
Okay, does anybody have a map we can use to give this talk?
Well, it doesn't need to be a map. It's compatible with any.
Yeah.
The talk is compatible with any.
So there is no need to.
So when I look at problems that
So we're like on the brink of publishing like in progress.
Oh,
yeah.
Well,
yeah. Yeah, are you busy this week, more or less?
I'm doing something.
Yeah, I'm actually going to a conference in Providence Wednesday through Friday, and then next week I'm going to be giving a talk at Brown.
Then you get the geometric action.
It's like an hour away, actually.
And then you get
Oh, yeah.
Providence. Providence. It's a university in Providence. So it's actually one of the Ivy Leagues.
You really take all the sounds action. You add all boundary terms.
I haven't been to Providence in maybe 15.
And then
Maybe 14 years, actually. The smallest, well, Rhode Island's the smallest state. Yeah, it's like a state right to the south of the nation.
And then you basically end up with the geometric action for GMS. That's roughly the story. What makes
I guess it's just like
is the way we did it.
throw a random dot at the United States. That's very much like that. Well, I am going to Hawaii in
and that was kind of necessary.
in 2013.
If you want to pay this astronomy,
Are you
and
guys?
plus computer definitions, you can basically geometric action for BMS. I think it's that's roughly the idea.
So why is it necessary?
It's like
Otherwise, like the original goal is.
Yeah, I'm not a fan of winter, so
Like usually just to describe us, right? But at some point you would like to describe us and scrum minus at the same time. And the rough picture that Walt had in mind was okay.
I mean, I'm sure it's not that bad.
So you're not looking at the cylinder with one boundary.
We're geometric and we're independent.
Are you? Do you have your documentation to go back and forth?
We do a couple of
So the rough idea is that you have this picture, and you kind of, I mean, very rough.
That's not how we
kind
work
of
in PhD.
bring scrum pluses, scrum
This is
minuses,
basically
also in a
exactly.
sense.
That was why I just
No, that's the idea. You want to
I want to see how the
you
other
want to
half
mimic
is.
Penrose.
You guys
You want to
only
mimic the
minus a
certain.
day.
You want to mimic the second boundary by introducing it basically.
Like with that extra day, what I could do.
So that's basically something that Walt is working out with Mark and the Rush at the moment with ADS. And that's basically working out for the baby.
All right. Thank you for your patience and sorry for the delay. Yes, thank you. Thank you very much. All right, so our final speaker for the day is Alfredo Guevara from the Perimeter Institute. Did I say your name correctly?
Yes. No.
All right. He's going to tell us about spinning black holes and amplitudes in quantum field theory.
Well, I know this usually is supposed to end at 2:30. So I'm gonna make it very light. You will have to forgive me that I don't give many details. Just mostly conceptual things. But if you're interested in the details, then I'm happy to talk after the actual talk. So I'm gonna talk about spinning black holes and amplitudes. So I work mostly on amplitudes. There's a nice program going downstairs about scattering amplitudes. So let me just show you, just to set some context, two claims. So the first one is that we know that gravitational wave detectors are incorporating higher precision measurements, and therefore we expect to need more precise templates for gravitational measures. In particular, analytic methods, such as the post-Newtonian expansion in particular, have been extremely successful for inspired phase of the measure. On the other hand, if you're asking now what is scattering amplitude, let me just tell you that the scattering amplitudes are the main or the most fundamental observables that we compute in quantum field theory. And starting from 04, thanks to the work of Witten and then Cachaso, Nima, who is here, and other people, we know that in many theories, the scattering amplitudes exhibit a remarkable simple structure, which is completely invisible from a Lagrangian starting point. So I won't say we're quite sure of why are these structures appearing, but we know that we can use this simplicity to boost perturbative, or even in some cases non-perturbative computation. So there are two things, so you may ask what's the relation between these two things. So let me claim the following. So the claim is that we can model certain kind of compact objects, such as black holes, as certain elementary particles, and we're going to use an approximation for a regime where these compact objects are far away from each other. So we're going to treat long-range interactions, such as gravity, in an effective sense, meaning we're going to neglect all the irrelevant scales. So just to give some pictures, I'm going to interpret this as a scattering amplitude instead of solving instead of solving Einstein's equations, which I would usually do for a 2D problem. I'm going to understand it from the perspective of exchanging fundamental particle, which is a graviton in this case. So this blob here, I'm going to tell you what is inside this in a second, but you just have to think of this as a coupling of this matter particle with gravity.
Are you assuming that they're coming from unbound states and ending in unbound states?
Good. So the scattering here is in red, so there has to be some subtlety, of course. Oh, okay, not yet. I'm going to answer that question in 2 slides. Yeah, so the second thing that you may ask is that, well, that's like the third thing that you may ask, but the second thing you may ask is, are we actually interested in this process, or are we actually interested in measuring this process? And I claim that in order to measure, what we need is to include external particles, such as an external graviton here, such that you have some flux of energy and momentum to infinity. So I'm claiming that, in principle, these two processes, conservative and non-conservative, should be enough to contain all the information we need in this regime. Okay, so the third question you may ask is that I'm considering scattering. So scattering is defined as something going in and something going out. In this case, I have 2 particles of initial asymptotic velocities, P1 and P3, or momenta. And they exchange some momenta, and then they go out to infinity with some of the momenta. Now, we're most interested, for in spiral phase, we are most interested in something going in and then keeping orbiting each other. So in this case, there might be a different scenario. But the claim is that these two processes, which are actually which both actually happen in nature, they contain the same information, and this is this goes back to the times of Feynman. So, and this is the one Torino paper. So what we do is we consider a scattering of 2 massive particles. In this case, these are electrons. We read off the scattering amplitude. It looks like this. There is some channel here, and what we use is the Born approximation. We Fourier transform the scattering amplitude with some normalization depending on the asymptotic states, and we read off a potential. And the potential we use in a bound system. In this case, I'm approximating, of course, because I'm looking at Newtonian physics, meaning I'm going to get the Coulomb potential. So I'm going to look at low velocities. And of course, this potential is exactly the same, or the claim is exactly the same potential that controls the two-way problem, independent of which trajectories you want to consider. Now, Feynman here was, of course, advocating for a space-time point of view. So he's saying that the simplification of these expressions come from a space-time point of view. That's actually very interesting, but the second claim is important, saying that the relation between this process with the previously known Hamiltonian formalism is actually straightforward to derive. So he was mostly referring to what we now call old-fashioned, or some textbooks call old-fashioned perturbation theory. So in this case, what we have is some potential, some Hamiltonian actually, and with this Hamiltonian we want to compute what we call the S matrix. So we want to consider this process where some initial state goes to a final state given a Hamiltonian. And we computed, there's a formula here, it's a perturbative formula. But now the question is, suppose I give you this S matrix, so the probability of this scattering. So how can we compute the potential? And then you try to invert this relation between the S matrix and the potential, and you find that you cannot. And the reason is that the amplitude itself, the S matrix is a gauge invariant object, it's unobservable, whereas the potential is gauge dependent. Now, what we do, what people who do usually, is to come up with an ansatz. So once you have an ansatz for this object, you just plug it in, and then you start matching coefficients and so on. So if you come up with a very clever answer, then your potential looks very nice, and you can do this at any order in the coupling constant. Now, there's also a subtlety that you need to take, the classical limit. I'm not going to explain what this is. There's a, of course, obvious subtlety because this is a quantum mechanical object. But my claim is that there is no conceptual deep meaning in this limit. It's just literally, if you are very careful enough, you can take h bar to 0 and you get the classical part of the potential. Now, for bounded orbits, which we're most interested in, for this potential, we have an expansion that we call the Poissonian expansion that arises because we're considering circular or quasi-circular orbits in principle, and therefore the velocity is of the order by the Pengyu theorem is of the order of this coupling. So Einstein, Infeld, and Hoffman, sometime in 1910 or something, they computed the first correction to the Newtonian potential, which is what we call 1pn. And you can see from here that the order in which this is based is g being roughly b squared. So this is 3 terms exactly because there are 3 choices of this quadratic order. This is for bounded orbits. Now for scattering, what happens is that really the velocity is a free parameter. So velocity doesn't have to have any relation with the coupling constant. So velocity is completely unconstrained. So what we have is only a perturbative expansion in g. If you just look at the previous answer, but you include all the corrections in the velocity, it turns out that you can resum that very nicely, and that's exactly what the scattering amplitude is doing. So the scattering amplitude is taking initial states, final states with arbitrary velocity, fully relativistic, and this is the answer that you will get at order g squared. So this is what people would call a post-Minkowskian framework, because it turns the G Newton perturbatively. It's mostly used for radiation. So if you want to study the fluxes at non-infinity, the multiple decomposition of the metric at non-infinity, the framework is post-Minkowskian. But my claim is that even for the conservative processes, we can think of this post-Minkowskian framework as encoding the post-Newtonian expansion. So in a sense, it's bigger than the post-Newtonian expansion, because these terms that you're considering here, the higher orders in velocity, they will appear at some point in the post-Newtonian expansion as well. So you may say, okay, in the scattering, actually, we can repack this information about the potential. So we don't usually compute potentials, we compute amplitudes. More physically or more phenomenologically, one is interested in the scattering angle. So, which I'm not going to tell you how to compute from the amplitude, but it's not very different from the fact that you can compute the potential. And that makes you think actually how frequent are these scattering events. So in fact, I mean, it's very unlikely to find a black hole scattering, or actually it's very hard to detect as black hole.
One very quick question. Where in this analysis so far have you included general relativity?
Good. So there is a non-shell perspective. I mean, there's a different perspective to general relativity that I want to advocate here, which is the fact that you don't need to start from a Lagrangian description.
I see.
So basically, what we're going to do is we're going to find what are the amplitudes without the need of a Lagrangian, and the fact that you have included an LCT2 particle, which is the graviton, will tell you exactly what the amplitudes are because of the aggregation variance. So I don't need to start with, I mean, the fact that Einstein-Hilbert Lagrangian is of that form is because of diffeomorphism. So this is all encoded in this perspective. Yeah. Now, just to mention a few instances where this scattering thing can happen, even though it's hard to detect for black holes. Like bending of light is actually one instance. So in the case where one of these guys is massless, you can think of light bending or light deflection as some scattering. We have also scattering of gravitational waves with black holes. That's or a scalar field with black holes. That's closely related to the Super Ryan's phenomenon. I'm gonna mention it briefly.
So I didn't understand your answer to Ramesh. So this is an effective field theoretical approach? Is that what you're...
It is an effective field theory, yes, but that doesn't have to do much with this question. I mean, it has, of course, neglected UV scales. Mm-hmm. But the main point is that we don't need to use, even though we can consider UV corrections to this, we can also include them without the need of a Lagrangian. So those are two different things. Okay, so I just told you that the post-Minkowskian expansion encodes the same information, resum in a nice way. Now you can see what's the status. Well, the status is that all these post-Newtonian terms here that are in green and also in blue, they are known. But in this case, if you look at this horizontal line, it turns out that, well, these horizontal lines are completely known. So all the orders in velocities are completely known. In particular, the 3pm, what we call basically the G cube order of the amplitude is known thanks to a very recent result by Bern and more people. So this horizontal line actually has the full relativistic expansion. Now, and this is, the claim is that this is what the amplitude will give you. After that, you can of course neglect these terms if you're not interested in more than 4 post-Newtonian. So, but they are going to be there if you need them. And the summation is actually more compact than the full expansion. Now, there is another word to this. There's a different level of complexity which has to do with the spin. Now, when you include spin, things start getting more complicated, so you have more degrees of freedom, and things are known, let's say, to a lower order. It's actually harder to tackle this problem to a spin. This is linear in spin, so there's an infinite tower going beyond this, which is all orders in spin. In the post-Newtonian expansion, they will be of the order of B something, but the point is that eventually we want to resum not only the velocity expansion, but also the spin expansion. And the reason for that is because we can. So I try to convince you. Okay, so why do we consider spin? Well, you probably know better than me, but just to set some ideas. First, thanks to electromagnetic observations, thanks to observing accretion disks, we believe that most astrophysical black holes are rotating, actually close to extremality. Second thing is that we know that certain spin compact objects can resonate with ultralight bosons, so especially ultralight scalars or massive spinning particles, and this will resonate. This will lead to the phenomenon that we call super radiance. And also, it happens that in the post-Newtonian expansion, the multiples of the source multiples of a compact object at high enough order in spin will allow you to distinguish between these two objects in the post-Newtonian sense. You can also distinguish them from finite size effects or tidal forces, but there's a nice way of doing it just by looking at the spin multiples. So it's very important to include spin in these computations. It's actually important to include them in the scattering amplitudes, and it's very natural to include them in the scattering amplitudes. Now, in order to include them in the scattering amplitude, we have to go back to what we understand by a Kerr black hole. So we consider different descriptions of it, and we try to find what are the correspondence between the first description. In this case, the first thing that, as a high energy theory, we try to understand is the causal structure. Actually, as Pengyu told us a couple of minutes ago, we are very intrigued by this causal structure of the Kerr black hole. And the second thing we try to understand is finite size effects. We try to model these compact objects as some rotating disk or something. And in this case, for the Kerr black hole, of course, you know there is a ring singularity. So the key element here is actually the radius of the ring singularity, which measures how fast is this rotating. So I'm going to consider a spin vector in the direction of the axis of rotation, and that is proportional to this vector A, which is the radius of the magnitude of which is the radius of the ring singularity.
Why do we care about this if we're expanding about a picture where the black hole is point-like?
Sorry?
We're expanding about a picture where the black hole is a spinning point-like object, right? So why do we care about this?
No, we don't care, but you should be worried that this picture is lost once you consider a point-like particle. So you may be worried what happened with the horizon or the aerosphere.
Yeah.
Okay, so you basically went ahead of me, but what we are going to look at is a picture in which we have some source, some word-line source in the space-time. You can consider an additional degrees of freedom, which is what we call the spin vector. It has some dynamical evolution, and this source will interact with gravity, of course, and will emit either some radiation or it will interact with another source. So the first thing I have to say about this is that this point of view, the advantage of this as compared to these two is that this allows us to treat perturbative computations. So we can plug, in principle, as many sources as we want. We keep solving Einstein equations, and eventually, if you have a lot of computing power, you will find solutions for the n-body problem perturbative. Whereas in this case, there is some magic related to the fact that the Kerr solution is integral. Now, the difference between these two things is that in this case, there's a point particle, in this case, it's a finite object. But in this case, you have to consider that this is actually encoded in the finite size is encoded in this spin vector. So I'm doing this multiple expansion of this object. Meaning first I'm going to have some monopole, dipole, and so on, which would eventually reproduce the full finite object. There is also a way of looking at the horizon, which is what you see in this perspective. From the perturbative perspective, I'm not going to tell you exactly how, but it has to do with summing eventually all order diagrams, so that you will find that if you are close to the horizon, the sum of this perturbation is not convergent. So that's a way in which this picture would reproduce these two other pictures. Now, there is something here interesting. So you have to consider when you solve these Einstein equations, you have to consider there is some off-shell modes, right? So roughly there is some graviton which is propagating to this. So let me make this more precise. So the claim is that, well, let me say that this perspective is called the MPD equations for rotating systems. I think you heard a little bit of that with Scott a couple of weeks ago. Now, you may say that there is some option modes here, but okay, my claim is that this object itself is equivalent to a 3-point amplitude, a scattering amplitude between one incoming particle of momentum P1, which is asymptotic velocity here, outgoing with P2 and so on. The field that I'm going to read off here is exactly an external graviton. Now the question is what happens with these off-shell modes? Well, they have to be somehow encoded here. Now, this is completely classical, and this, in principle, has to reproduce this. That means that this perspective on off-shell gravitons have to have an exact analog in this blob. So the blob basically will have to have loops. So that tells you that things that we learn in grad schools, such as the number of loops goes with h bar to the L, where L is the number of loops. That's completely, I'm not going to say it's completely wrong, but this subtlety is, it's a subtlety. So in principle, there can be loop contributions which are completely classical. And we know that thanks to the work of Duff and other people. There is a small subtlety where you have massive particles interacting with masses. Okay, so the next question is, what is the meaning of this spin vector? So we have this degree of freedom here. What is the meaning from this scattering amplitude? So this 3-point amplitude should have some spin vector. So the example that I'm going to use to establish this analogy is mostly QED. It's not really QED because this is going to be classical, so it's electrodynamics. But we start from a field theory Lagrangian. So this is the Dirac Lagrangian, and then you have this G-2, which is what we name magnetic moment. And this represents some kind of non-minimal coupling. So the minimal coupling defined as covariantizing these derivatives is obtained by G = 2. So this is a standard effective field theory, and then what we do is we compute the amplitude of this. So we read off this field here just by computing the 3-point vertex. This is a linear theory, so there is no loop corrections. This is exact. And what we find is that it has two pieces. One piece is roughly a scalar piece, and the other piece is a dipole piece. And the dipole, of course, is proportional to the magnetic moment. So the way the spin couples to the photon is proportional to the magnetic moment, so almost by definition. Now, this has two ways of writing it. So one way is it has sign ambiguity depending on the helicity of the photon, and the other way is more general. The question is, what is A here? Well, A is what we define as the Pauli-Luansky vector. So this has some angular momentum here, exactly this coupling here. And from this you can define this operator. But the subtlety is that you define the operator with respect to a reference momentum that's neither P1 or P2, but for instance some average moment. So the spin operator is going to be defined with respect to this. Okay, so you compute this. This is a 3-point amplitude. And now the question is, what is the word line description? Exactly the right-hand side, right? And the word line description is exactly the one that gives you the same amplitude. So if instead of having field theory, you consider a word line coupled to a photon, so this is standard coupling, and then there's some non-minimal couplings. And A is a dynamical parameter, so it's some internal degree of freedom. And you consider, again, the interaction between these two, you will find these two terms. And it's exactly the same amplitude, but the description, so the underlying description now is a word line description. And this is a model that Bergman, Michael, and Pilecki introduced for a classical electron. So they wanted to understand the precession in a classical point of view, the spin precession. Okay, so here's the main claim that I can do now that we have seen this analogy. So the first claim is actually very old, or at least intuitively, is that the jth intrinsic multiple, so the jth power of the spin vector in an amplitude, can be obtained by scattering a particle of spin s, which is greater than j over 2. So if you want to see a quadrupole moment, you have to consider at least spin 1. So that's the standard law that electrons do not have quadrupoles, and the reason that they do not have is because when you square A, you get something which is proportional to identity. So roughly, you have only the monopole and the dipole, which are these two operators here. You keep squaring, and you don't have enough degrees of freedom to have a quadrupole. Okay, so the second claim is that spinning black holes, more precisely black holes, are in correspondence by 1, so by the first claim, to massive particles minimally coupled to gravity. Now, the example for that is that the Kerr solution, if you consider the gravito-magnetic moment of the Kerr solution, so you have to decompose the gravitational field into electric and magnetic pieces, you can evaluate this object and you will find that G is 2. Now, it turns out that this is a slight overstatement, so G is actually 2 in most of the solutions for general relativity. But the point here is that I'm using the intuition, so we really don't understand why is this true, why black holes are reproduced by minimally coupled particles. But the claim is that at least there is some intuition in that black holes are not, they are not supposed to have hair. So they are not supposed to have any additional parameter. So G here, which is a parameter in QED, should not be a parameter in gravity. Now, that tells you that there's only, yes?
How many parameters would there be in coupling in the coupling to gravity of a generic spinning particle?
Depends on the spin, but it starts up.
It grows with the spin?
It starts before, after this, so the quadrupole will already have a free.
2s plus 1.
Yes.
Yeah. 2s plus 1.
So the quadrupole will also have a free.
So you're saying here there's some special simplification for the couplings to a black hole?
And it's related to the no-hair theorem.
Yes. Well, intuitive. Okay, so thanks to the work of Nima here and his friends, it is understood how we can construct, for any spin, the amplitudes for minimally coupled particles to gravity at the linearized level and without the need of a Lagrangian. Now, the answer turns out to be extremely simple, or at least can be written in an extremely simple form. You see that the only parameter here is A and M. So this is exactly what I meant in the previous slide. And the answer for minimally coupled particle turns out to be, you can resum that into an explanation. So it really looks like the previous answer that I showed you for the QED, where you set G to 2 and then exponentiate this. This form depends on the helicity, so there's a plus and minus here, but you can also write it if you expand the exponential of this object as cos plus sine, and then you manipulate a little bit the sine piece. You can expand it in such a way that it doesn't actually depend on the helicity, and this is very important. It's exactly the analog of what I did here. Now, because of this amplitude, we can now consider what's the field which is being emitted from this particle, or from a Kerr black hole, and we find that the field actually takes a very nice form. So we Fourier transform, or when we Fourier transform, we replace k by derivatives, and then when we put a propagator, of course, because we're looking at the source and how it propagates, we're going to replace the actual channel by 1 over x, so we're going to get this factor, and we expand the exponential in 2 parts. Now the first part, what you can see here is that it's proportional to p mu, and the other part is transverse. So the first part, what tells you exactly is what is the static potential that a particle going around the curve black hole should feel. And you can compute it, you just project this with p nu, and you find out that the potential can be written in this very nice form. So this basically will do a shift in the Newtonian potential that takes this form. So this is what we call the Newman-Yanis construction of the Kerr metric. It's actually true to all orders in the Newton. And the reason for that was pointed out by Kerr, sorry, by Newman and Yanis, who were the ones that introduced this deformation. So in a private communication, what Kerr used was the so-called Kerr shield form of the black hole. And he found that every time you have this Kerr shield form, there's only the need to compute just the linearized perturbation. So exactly this order in order to find the full metric. So there is a special integrable property about this Kerr solution. And this has also been explained in the recent paper by me. Now, of course, what we want, I mean, this already provides a new insight of the Kerr solution. So as Nima has pointed out, this somehow explains the underlying reason behind the Newman and Yanis construction. But what we really are looking at is exactly to compute, we're looking at the 2D problem, right? So the advantage is that now we can do a 2D problem very trivially. We just need to glue 2 of these objects. So we found the Kerr solution, and now what's behind, what's beyond the Kerr solution, meaning 2 actual rotating black holes, is just a perturbation theory with this vertex. So I glue these 2 objects. I don't need to consider any test limit, any extreme mass ratio limit, and so on. I just need to glue these 2 objects, and I will find that the exponentials basically commute with each other. And there is a very nice phenomena here that was observed in the effective one-body construction, that basically you can move all the spin from one particle to other, so you can make one particle spinless, or you can make the 2 particles spinning, and the effective potential will be the same. So there is effective one-body phenomena here, and this will also have some effective one-body interpretation. You can consider a test geodesic in Kerr with no spin at all, and that will have the first post-Minkowskian order, it will have the full information of 2 rotating black holes.
How should you think about the symmetry that enables you to do this shifting of the spin between the 2 particles?
Sorry? How should we think about the symmetry?
I mean, the symmetry that says that the amplitudes are the same.
Yeah, so that's called an EOB symmetry. We understand, I mean, this part, the scalar part, we understand it from a high dimensional embedding, as Simon has shown, Simon Caron. So this part, the symmetry is actually a Lorentz symmetry, but in a higher dimensional setup. We don't understand exactly the part that has to do with the spin, so that's like one of the current problems. But this already tells you that there is some interesting phenomena that we have to study. Now, the second observation is that, of course, it's at 1 p.m., so at 2 p.m., effective one-body breaks down. What doesn't break down is the p.m. effective one-body, but the 2 p.m. effective one-body, the Minkowskian one, does break down. We don't understand also why, but it doesn't really matter because we can compute it anyway. So we can compute the scaling amplitudes with any mass ratio without having to resort to any effective one-body technique. And the claim is that not only the conservative piece can be included, but also the non-conservative piece, as I showed you a couple slides before, can be incorporated just by including these higher multiplicity amplitudes, so more external gravitons, and you will find that actually when you take the classical limit of this object, there are some classical pieces that come from the loop. So this loop here will also have some classical contribution. Okay, I think that's most of what I wanted to say, but let me just leave you with this roadmap of what is left to explore between the black hole merging phenomena and other aspects of quantum physics.
Right, questions?
You were talking about resumming perturbation theory and seeing the horizon within your framework?
Yes.
Right? So was that done only for Schwarzschild or also
Yes,
for Kerr?
it's done only for Kerr.
Would you expect, I mean, in principle for very high spin, near extremality, you also have very, special things happening near the horizon. Would you expect to see that in a perturbative resummation of the spin expansion, or would that be non-perturbative?
What kind of special things?
I mean, there's this near horizon geometry.
Right. You're talking about near extreme and near horizon.
Right. Do you expect to see that if you can resum the expansion and spin somehow, or would that be non-perturbative?
What I can tell you is that in effective field theory, you can consider different regimes. So this near horizon extremal Kerr metric is one regime, which is related to a near zone, and there is also a far zone regime. So there is the buffer zone, where you can actually match these two regimes. So basically, that tells you that there is some way of getting information of the near zone, just from. I'm not sure exactly if you can approach to the near horizon method, but there has to be some matching procedure relating the far zone information, which is what we mostly look at in this perspective, without having to go to the full non-perturbative ability.
Ramesh?
So I want to go back to this very basic thing that I'm still confused about.
Yes.
So you don't use a Lagrangian, you don't
No.
use Einstein's equation,
No.
there's no space-time curvature.
No.
You're just scattering in flat space.
Yes.
And the results are equivalent to general relativity. It's because your interchange particle is a graviton, spin 2, whatever. But still, it gives GR, it doesn't give some other theory of gravity. So how does it know it should give general relativity and not something else?
Okay, that's a good question. So up to this point, it's really it's not relevant, because this is just a 3-point amplitude. So basically,
Sure.
the equivalence
These
principle.
guys.
Yeah, the equivalence principle will tell you anyway that this is gonna be that thing.
Mm-hmm.
When you come up with these guys, so these are actually higher curvature corrections. They can include higher curvature corrections. They will have an ambiguity. So they will have extra, when you want to constrain them, just from the fact that you have these LCT2 particles with some matter particle here, you cannot constrain them precisely. They will have extra coefficients.
I think he's asking a different question. I think you're answering a different question. I think he's asking, even before worrying about higher curvature corrections, the sort of more basic question: how, from just thinking about consistent scattering of gravitons in flat space, how do you know you get GR rather than some other random theory of gravity? And it's sort of implicit in the entire construction that just special relativity and unitarity
and spin 2
is enough to guarantee it has to look like
there's
GR.
only one
So
form
there's only
of
one
gravity.
theory. There's only one
Oh, I
theory.
see. Yeah. So you're not asking about.
He's not worried about R squared correction.
This was Feynman's old.
Okay.
That was probably Coimbra
So
as
to
well.
get any other theory of gravity, you have to have also spin 1 interchange or spin something else.
It's either nonsense, or if it's not nonsense, it's just additional degrees of freedom, like scalars or extra vectors.
Okay, something like that. But if you have only spin 2, there's only this one theory that works. Okay, fine, thank you.
Well, after you go to certain energy scale where you actually need to include this higher.
So this is an analogy to electromagnetic QED versus classical electrodynamics. And one of the issues that was dealt with by Wheeler and Feynman early on was the self-energy of particles. How do you solve it with gravity?
Oh, with gravity.
The self-energy of the black hole, so to speak.
I would say the same way as Dirac solved it with classical, with classical electrodynamics. So Dirac considered a subtracted version of the stress energy tensor.
And that's what you do?
Well, as of this, I didn't consider radiation. But when you consider radiation, you can actually extract the radiative part without self interaction. So So there is like one homogeneous and inhomogeneous solution of Einstein equations, and for computing this flux of energy momentum to infinity, you neglect the inhomogeneous field. Yes.
So everything you said has been about matching to classical GR.
Yes.
But I'm just curious about an actual quantum gravity question here. So the 3-particle amplitude for 2 black holes and a graviton,
Yes.
as you say, is minimal coupling. So just like we can calculate in QED, we can calculate G minus 2 as the leading, completely reliable, finite correction. Do you think there's some calculable loop corrections to the 3-point amplitude for 2 black holes and a graviton, which will be finite, and and do you have some?
Yeah, sure. Sure.
I mean, it should be calculable. It's just the same way.
It's exactly it's just the same way.
So they're tiny, but those are the genuine, honest quantum gravity predictions.
That's
totally
how
calculable. Right.
That's how this whole program started by.
No, except but the program that you're about to say involves logs, right? So there are some. This would be completely finite, I think.
Yeah.
Dead finite, completely finite, just like G minus 2 for the electron.
I mean, the program I was about to say that was introduced by Donoghue in the 90s.
Right.
That was without spin, so he was for sure not looking at.
So there are things like that. There's logarithmic corrections to black hole entropy. Those things, the coefficients of the logs are calculated. That's already cool. But this would be some dead finite thing, which would be 0 classically and non-zero quantum mechanically, and you could just compute it. I think it would be cool to just compute
that's
it.
actually. Yeah. I'm not sure how sensitive, how neglectable it would be, but it might be observable.
Okay, Andy, one more.
Can you see bound states in this picture?
Right. So that's what you would do back here, right?
Yeah.
So what you do is you compute scattering amplitude, and once you get the potential, you just plug it into Schrödinger equation. So in that sense, there might be a way of looking at the same analog in gravity. I'm not gonna. There are another kind of ideas, but I'm not gonna. I can probably talk to you later. Okay. But roughly, the first thing that one would try is actually to reproduce this line of thought, in which once you have the potential, that should be enough to look at these bound states.
Okay, guys, with that, let's call it a day and thank all our speakers.
Actually, there's a bank where you're